this video, I want to walk through an example of using projectile motion to solve a problem. And I've talked previously about how there are some assumptions that we can make, or we often make, when it comes to projectile motion. And those two main assumptions being that there is constant acceleration in the vertical direction, and that as long as this thing is not being accelerated after its initial launch or throwing or whatever, that there is constant velocity in the horizontal direction. So I've set up a little problem here which basically shows a ball being fired out of a cannon or something. And there's some initial conditions. The ball is being fired initially from a height of 2 feet. And it's angled at 40 degrees, and it travels until it strikes a point on a hillside at 3.5 feet high, not much of a hill, and it's 14 feet away. So that's what we know about it, and to solve this problem, we want to solve for the initial velocity that makes this happen. The change in distance of 14 feet and where this ball eventually lands. So if we were thinking about this as an experiment that we were observing, we would know everything that the setup ahead of time. We'd know this 2 feet. We might not know the 3.5 feet until the ball lands. We'd know the initial 40 degrees, and we'd be observing how far it travels, this 14 feet. And it just so happens when it travels that far, it strikes some elevated location at 3.5 feet. So we can start listing out the things that we know. I'm going to define a coordinate system, not anything too surprising. I'm just going to define an XY standard Cartesian coordinate system for this. So the things that we know that it travels some distance in the horizontal direction, which we've defined as the x direction, and therefore we can say that delta x is equal to 14 feet. Similarly, we know it undergoes some change in position y, and from start to finish, that is a positive 1.5 feet. We know that it has an angular orientation, initial angular orientation of 40 degrees. We know something about the acceleration, right? And that is that it is subject to the downward acceleration of gravity. So we can define a y as g as negative 32.2 feet per second squared. And for completeness here, we'll say that the acceleration, the x, is specifically 0 because there's nothing acting on it in that direction. Of course, we're neglecting things like wind resistance and so forth, but that's fine. We can say that that's 0. The other bit of information we know is that, or that we don't know maybe, is v naught, but we can break this down, and we're going to define for ourselves v naught x is going to be equal to v naught, and then using geometry, cosine of 40 degrees, and similarly v naught y is v naught sine of 40 degrees. So we've got some equations. Great. Now, I said at the beginning that we knew that we have a constantly accelerating motion in our vertical direction, which is our y direction, and we have a constant velocity motion in our x direction. Now, what that does for us is it provides some simplifications that we can make in terms of our equations. So our equations that are useful are recalling the equation that drops out of constantly accelerating motion is y equals y naught plus v naught specifically v naught y in this case, times t plus 1/2 ay t squared. So this is constant acceleration, or that's where it comes from. X equals x naught plus v naught x times t, and this equation comes from our constant velocity assumption. So we can start plugging things into these equations, right? And what do we know from these equations? Well, once again, we know the acceleration. We define that up here, ay. We don't necessarily know y and y naught, but what do we know? We know the change, right? So if I subtract one of these over, that's fine. I can plug in this number, 1.5, for the both of those together. Same thing in the x direction. So I can rewrite these equations with the numbers that we know, starting with the y equation, 1.5, which is delta y, equals my initial y position, which I'm going to define as where the ball exits the barrel of this cannon. So that'll be 0, or excuse me. Oh, yeah. So our remaining terms then are v naught sine 40 degrees. So this is our v naught y. And that all gets multiplied by t. And then we have acceleration in the negative direction, so negative 1/2 times 32.2 t squared. For my x equation, I have a delta x of 14 feet, which is then going to be equal to my v naught x, which is v naught cosine of 40 degrees times t. All right. So to solve these equations for my unknowns, or maybe better I should say, well, what are my unknowns? My unknown values, as we can see, are t and v naught, right? So I'm going to start by taking this equation, and I'm going to rearrange that and say t equals 14 over v naught cos 40. And I'm going to take that and I'm going to substitute it into my other expression. So I'll pull down my other equation, and I get 1.5 equals take me a second to write it out here. All right, so doing some rearranging here, I have in this first term, I have a v naught in both the numerator and denominator, so those are going to cancel out. 1.5 is still here. Sine over cosine is tan 40. And, oh, and I still have 14 here, so I'll write that out front. 14 tan 40 minus 1/2 times 32.2 times, and then over here I have 14 squared, which is 196 v naught squared cos squared 40 once I distribute that square into the problem. So now the only thing I have left in here is a v naught squared term as an unknown. So I can go ahead and rearrange this equation and I'm just going to rehash all my numbers here, 32.2, 196, cos squared 40 divided by okay. So I think I've got things rearranged, and then I can go ahead and solve this problem, take the square root across, and end up with v naught equals 22.9 feet per second. So that allowed me to solve for that unknown value. Of course, in the problem here, I had two unknowns, the second being my unknown time t. We weren't specifically looking for that, but if I wanted, I could take this v naught and go back and plug it into this, this equation here and solve for t if that was something that I was looking for. But what this has told me is that my initial velocity of that projectile of 22.9 feet per second is what caused it to travel that distance of 14 feet. All right, thank you.